All right, so it is my pleasure to introduce today's speaker. I started the doctoral program at CMU in 1997, and I feel very lucky to have been at CMU at that time. When I think about the people that I got to hang out with at the time, I mean, they changed our field, like Frank Dallaire and Chris Urmson and Joël Pineau and people like that, and of course, Vandi. And I remember meeting Vandi when, so the way the program works is the beginning of September, all the incoming graduate students, so like we have a big social, we get to know each other. And I remember meeting Vandi, and you could tell like she was already a force of nature, and she was gonna have tremendous impact on all the things that she did. I remember like Mike Montemerlo and I, on the weekends, we'd maybe go get a burger at Silky's in Squirrel Hill, would maybe go bowling. Monday morning would come in, and Vandi had spent the weekend climbing a mountain, and had spent like 2 days sleeping in a bivouac on the face of a rock, and that was just amazing. Or she would spend the weekend getting her motorcycle license. And these are dangerous pursuits. Spending 2 days sleeping in a bivouac on the surface of a mountain, or like motorcycles, are very dangerous. And so Vandi, being brilliant, merged her sort of hobby activities with her research. And her research, I remember the paper that she wrote on risk-sensitive particle filtering that showed new ways that we could actually accurately estimate the really dangerous things that might happen, which tend to be relatively rare, which is hard to do with a particle filter. And then, so Vandi had an enormously successful PhD thesis in fault tolerance and went off to NASA, first to Ames, then to JPL, where she's now one of the drivers of the Mars rovers, and in fact, the deputy director of the robotics program there. And once again, Vandi's passion for these very adventuresome pursuits, combines with brings risk, and she brought that again into her research. I mean, it's hard to imagine, a system that is more or less risk tolerant than a rover on Mars, where the round trip time can be anywhere, actually, Vandi's going to talk about the round trip time to Mars, so I'm not going to spoil that. But when you think about how hard it is to actually drive these complicated systems and make them work so robustly, it's because of the work that Vandi, and of course all her other colleagues, have done. And so I'm just enormously proud to have known Vandi for all these years, been amazed by the things that she's done, and I can't wait to hear in more detail. So without further ado, Vandi.
Thanks, Nick, for that introduction. It's actually been really great at this conference to see so many old friends and to meet a lot of new students. There's just so much excitement, and to see a lot of the work that's going on. So today, I'm going to be talking about the autonomous NASA mobile robots we have on Mars, and how the autonomous capabilities, which is something that I'm particularly passionate about, are impacting what is possible in the future. So this image here, so for the past 14 years, I've been working on mobile robots on Mars. And so this image shows some of those robots in NASA JPL's Mars yard. You're seeing, many of you already know, in the front and the left image is the Sojourner rover, which was the first rover we sent to Mars, and that lasted 87 days. And on the left is the Mars exploration rovers. We had 2 of them, Spirit and Opportunity, and they were meant to last 90 days, but Opportunity explored for 14 and a half years, and I was in grad school when it landed. I didn't think I'd get to drive that rover, so it was really exciting that it lasted that long. And then in the middle is the Curiosity rover, and it has been on Mars for 10 years and is still going. And on the right, you see these are full-scale Earth replicas, and that's why I put them in this image. You can see comparatively, the size is growing.
Sorry, just
Thank you.
So they can hear you a little bit better.
Okay, great. Am I not? Okay, I will try. So that image is of the Perseverance rover, and this is an early image of the test bed. We didn't actually have the robotic arm on the rover at the time. The robotic arm is very similar to Curiosity, but it has a much bigger payload at the end of the arm, a 45-kilogram turret, and the arm is 2.1 meters long. And the rover itself stands about 7 feet tall. And last but not the least is the Ingenuity helicopter, the Mars helicopter. It has a wingspan of 1.2 meters, and it weighs just 1.8 kilograms. So these rovers, it's still only 50% of the missions that we send to Mars make it successfully to the surface. So a robot that we have on Mars is a very valuable asset. Scientists really are looking to answer the question, could life have originated anywhere else in the universe? And one of the places that can really help with that is Mars. We believe that Mars once was very much like Earth. There was a lot of water, and it could be habitable, and it preserves those signs of life that are 3.6 billion years old, closer to the surface. And so they wanted to go to Jezero. And even though our landing ellipses are getting smaller, the one for the Mars exploration rovers was 200 kilometers, and Perseverance is 10 times smaller than that. It's still the case that it had this ancient river delta. That's why we wanted to go there. But it had crater walls that were tens of meters tall, so it was pretty hazardous if you were going to end up landing at the edge of a cliff. So the first part of autonomous capabilities is if you can solve a problem that is impossible to do otherwise. So solving something. So here's the case where the way we land, it's 7 minutes. So you enter the Martian atmosphere, and from the time you enter, the parachutes deploy, and you release the rover on its wheels onto the surface of Mars. It's 7 minutes. During this time, there is no Earth communication you can have, so there's a lot of risk. And so the only way to solve this problem was to add technology that could make something possible. But at the same time, this is what we call a Class B mission at NASA, where it's a national asset and the risk is really high. So you have to have the technology be provable such that the risk is reduced to that level. And the capability, that autonomous capability that enabled this to happen was called terrain relative navigation. So as you're landing on Mars, while it's on the parachute, it's taking images off the surface and comparing it to a map. And once it's able to localize, if it detects that's a hazard, which in this image it's showing that it was headed towards a hazard, it'll do a divert. These are images of what happened on the day we landed on Mars, taken with the camera, and you're seeing it doing landmark detection. And so in the green are all the inliers, the blue is the excess, and the rest is the outliers. And as the parachute is swinging down and bringing us into the atmosphere, it's tracking. And there was a lot of wind that day, so it was actually drifting us in one direction. And as you will see, it continues to track, and then it finds a successful solution. And then when it found a solution, it actually detected that we were headed for a hazardous zone. So it ended up doing a divert. And this is a video taken. For the first time, we actually had images taken while we were in the process of landing. Let me see if I can get this video to play. So this is, we had cameras which were looking up at the rover. Maybe it won't play. We had cameras that were looking up at the rover and looking down at the descent stage, and took an image as we were landing on the surface of Mars. And you can see on the right side of this video later on, if I can play it in this time. Oops, got me out of the presentation mode. Let me get back in. So that is the day we landed on Mars, which was February 18th of 2021, which was a very exciting day. And we knew where we had landed, because before that, you have the entire landing ellipse, and as a surface person who, navigating the rover, you don't actually know where it's actually going to end up. The location that it landed, we called the Octavia E. Butler landing site. And now, because TRN had diverted us away from the surface, we were on the other side of the delta from this hazardous zone. And we were going to have to navigate around. The green path shows some of the paths we were looking at that we were going to have to navigate around. But the reason we were going to Mars, one of the biggest reasons, is Perseverance is going to collect intact cores from inside the surface drilling and cache them. And so we wanted to collect a diverse set of samples and already knew we were going to be doing a lot of driving. One of the challenges with Mars is the latency in communication. So Mars can be as far as 250 million miles away. So it can take up to 24 minutes for a one-way lifetime signal to go there. And once I was thinking of how far is this? So if you were to get on a commercial airliner and fly around the world, and if you didn't have to stop or refuel, you would be doing that for 60 years to cover that distance. And that's how far it is. So we actually transmit commands directly to the rovers, but we take so much data. So that's a small amount of telemetry. We transmit the information through the Mars Relay Network, which is orbiters that are around Mars through the Deep Space Network back to Earth. So we get one uplink typically on a day, and we can get multiple downlink passes. But that means that we only get to tell the rover something different or have impact its decision once. The other challenge in this, and didn't intend for everyone to read the graph, but on the left, you're seeing all the sequences of activities from a plan that we did. This is just a fragment of it. So pink is showing the uplink. This is when we get uplink to Mars, and then the green is the downlink pass. So you only have the time between it to drive. But Mars is actually a really cold place. So one of the challenges we face is we have to heat the actuators. And energy is expensive. So the trade-off is, should you spend the energy just waiting later in the day so it's warmer, or should you heat the actuator? So you're seeing here the black, there's various activities that have to occur, and the green is the autonomous drive. So on a good day, you get about 2 hours of driving time, and that's it. And then the parse is going to come down. So the next point I was going to make is you can have autonomous capability that can do something, but it doesn't just have to do something. It has to be better than the human. And I'm sure all of you have people in your lab where if the robot does something unusual, they can figure out a way to make it do something and do what is intended. We have a lot of those people. And so because we're going to constantly encounter situations that we hadn't anticipated, if the autonomy isn't able to keep up with it, you're not going to use it. So in order to have navigation really work for us, we made some of strategic changes. So instead of just improving all around, what are some of the changes that actually made a difference to driving faster? So one was straddling rocks. Previously, we would use the entire rover's footprint and look for obstacles in that area. But we started straddling rocks. And then, we have the way we do autonomous navigation is we have the classic local path planner and a global path planner. But in the local path planning, we started doing more complex search so we could navigate more complicated terrain. And then also, there's just a lot of sand on Mars. Every drive that you do, you have to look into state estimation, and just doing wheel odometry isn't sufficient. We do visual odometry, where we are using images to track our position. And in this capability, we were also doing predictive slip estimation, so we could, while the wheels are turning, estimate and navigate hazards. But it isn't just the algorithms and the software that need to be improved. Also, a lot of systems engineering that wasn't sufficient. How do you make it faster when mechanically we weren't going to be able to, for the constraints of the mission, which is very real in the Class B missions, we weren't going to be able to change the rocker bogie suspension and the 6-wheel rover that we had. One of the reasons we didn't use autonomous driving a lot in Curiosity was the wheels started showing tear. So there were these really small rocks, not geometrically a hazard, but they were ventifacts. They were really sharp and started piercing the wheels. And we started seeing wheel wear, so we had to now navigate, so we were accounting for that, something that the autonomous system wasn't designed to do, and that's why we used it less. The wheels were redesigned in order to be able to handle much hazardous terrain. And this was done, actually, we 3D printed wheels, because these wheels are machined out of a single piece of aluminum and are fairly expensive to do a lot of different tests, and then ran a lot of tests in simulation and in the Mars yard to see what designs would best work. It was actually thicker wheels, larger diameter, and different Grouser pattern was some of the elements of that. The other thing we did was the navigation cameras. We used to have a narrow field of view 45-degree camera, but you had to slew it to take enough wedges with that camera so you'd have enough to cover the rover's footprint. With a wider field of view, you can cover the entire footprint, and also faster exposure. So as the wheels are turning, you can take the image and have faster processing. And one of the most important is just the computing. So we have a really slow processor. We have to have radiation-hardened computers. So we have a RAD 750 163 megahertz prime computer that we use to do all of the rover processing. We added a co-processor and a dedicated FPGA to do the vision processing, which allowed it to be a lot faster. And that is what was also used in terrain relative navigation as we were coming down, and after we landed, it was a dual purpose, and we switched it to using it on the surface. So all of this actually resulted in us being able to get really speeds that were desirable and comparable to what humans can do on Mars right now. This is one of the early drives, the Sol 200 drive, where we drove around Arby Ridge, and you're seeing the images that were taken with the onboard camera. We actually don't get to get down all of the data from Mars that is just engineering data, because it's competing with science data. And on the bottom right, another thing that autonomous navigation has to do at the end of it is autonomously figure out what heading to point to so you can communicate with Earth. If the autonomous rover gets into a situation where we lose communication with Earth, we do have fault protection, but if you completely lose communication, that's the end of the mission. So it also has to, the high gain antenna has occlusions from the rover's body. The Earth can be very low in the sky depending on where Earth and Mars are. So the longest single sol drive, a sol as a Martian day that we've done, is 319 meters, and in a single plan, which was over a weekend, so you uplink a plan and you're not actually sending any new information, you're just getting more days. So you're getting more power and energy in daylight times when there is enough heating. We've done 528 meters. And there's another type of driving we do where we don't get to get communication passes to uplink new commands to Mars, but we just string these drives together by planning on multiple days, and we've done 700 meters. So this for Mars is records. For Martian driving, these are the Mars records at the moment. This chart shows why we are actually using so much autonomous driving. So the left one is the drive sols along the x-axis, up to 200 it's showing only, and on the y-axis on the left graph is drive distance, and on the one on the right is time. And by driving autonomously, we're not actually slowing down that much. And that's really important, because if you slow down, then there's a trade-off, because if you drove over multiple, say, manually with humans just as far as the horizon can see, you could do more science. And so we're doing 80% of the driving with autonomous driving and 90% with mapping. And you're seeing these grades. So the blue is directed driving from Earth, and you know, it's still autonomous execution because you send the commands and you don't actually get to hit the emergency stop. And the orange is autonomous. And there are various different modes where it may do mapping, and you've chosen the path, and it's just checking that's okay. And so those are also very helpful to have these various knobs. But then there's other things people can do when you're driving, is we are characterizing the surface as we're driving to see how it's varying, what the differences in Mars are. On the mast, we have an instrument called the SuperCam. It has a spectrometer, so it shoots a laser on surface features like rocks, and the plasma that comes from that, it studies it with the spectrometer, with a telescopic imager, in order to look at the chemical composition. And there's a microphone, and so the pop of the laser also provides us information and tells us information about the rock. So these are really narrow field of view. That's a 5-centimeter image, and we were trying to actually catch the edge of that rock. And that's a drill hole, and we shot the lasers inside it. When you're driving and you blindly try to shoot, you're not going to get features of interest. So this was something the scientists are really concerned. Now, you're driving really wrong. That's all well and good to get to the next destination, but I'm not getting science done along the way, because for this, you actually get an image down on Earth, they pick that specific target, and then we precisely target it. So we developed autonomous capability, which does autonomous targeting. So you're seeing on the left there, the top left, take a wide angle image, and in the image, use techniques to find features of interest. So the scientists specify from the ground criteria that they're interested in, and this can be different for different terrains. And so they might be looking at rocks that have a certain shape, a certain brightness. And so once it's found that, it prioritizes them and will autonomously shoot it with a laser. There are other challenges that come about with this. You know, the robotic arm, we don't try to do one thing at a time. We're doing multiple activities in science. It may have faulted right in front of the laser, and you could shoot the robotic arm. So we do collision modeling, and we treat the laser beam as a collision object, and we're able to detect when it collides and avoid those collisions. Once you've picked the target you want to shoot, just getting a mechanism to precisely point at it also has challenges. So we use closed loop pointing with vision to precisely get the targets that we're interested in shooting. And this is a result from Mars where you're seeing that the center of the image is where we might have shot, which is just sand, and it is able to pick more interesting features, and we collect considerably more science when we do that. When we landed, this is showing the landing location, and then we drove to do the SETA campaign, which is on the south. So you're seeing the region where we did the little loop around the south and wanted to characterize the crater floor before we went off to the delta. Once we had finished that campaign, in the orange, I'm showing the two ends, we did a rapid traverse, and in a few weeks drove 5 kilometers, which for Mars is considerable, just doing back-to-back autonomous drives. So that's really what we want to do, is drive fast between locations and spend more time doing science investigation. And at this point, it's driven about 11 kilometers, and Ingenuity has had, and the green path is showing Ingenuity flights, and it completed its mission for doing a technology demonstration. We now use it for scouting ahead, looking at places that we might be interested in, so that we can drive the rover to do some of the science there. But really what we're going to Mars to do is in situ observations with a rover, and so placing the robotic arm in close proximity with the surface and abrading. So the wider hole there, we abrade the surface because the surface that is exposed doesn't have as much information, it's weathered away. We abrade it away, and then we can place instruments. And they need to be placed within centimeters off the surface, and the robotic arm has uncertainty. It's a 100-kilogram arm, and so we have to compensate for that. So we have a lot of techniques where we take images of the surface with the cameras mounted on the arm to reduce the uncertainty, because the robotic arm repeatability is much better than the end-to-end accuracy. Another reason that we sometimes stop using the autonomous capability is if something changes, and now you have to write new software. And uploading new software, which we do, is a much bigger endeavor on Mars. You're hot swapping, you have to have a running spacecraft all of the time. So autonomous capabilities really need to be reconfigurable. And some examples for why. So we had drilled, we have scientists, hundreds of scientists actually, 400 to 500 scientists from all over the world who are experts in planetary geology and astrobiology. And they gave us the rock cores that we should drill, and we had drilled a number of them. And we go to Mars, the very first rock we drill, the drilling all works fine, but there's no core. It was empty. And part of the reason was that we do have feedback, and the rock was hard. We'd abraded it and detected that, and there were pieces that were hard, but they were pulverizing. So it just pulverized. So it was just, we're going to Mars, it's going to be different. So it was very different from what was expected. Another example is with the bit carousel, where here you're seeing an image with the robotic arm on the outside, and there's a bit carousel on the front of it, which docks with it and transfers the bits and the tubes into the second robotic system, which is inside the rover's body. In this image on the left, you're seeing the robotic arm docked, and you're seeing at the bottom the robotic arm that's inside transferring the tubes. The center image is showing what happened, which was not supposed to happen, is there's a drill core on the top right, and it had crumbled, and there were pieces of it in the bit carousel and pieces of it in the drill. We were able to rotate it and drive and get those out, but we had to change some of the ways. We were actually moving the drill before we were docking because there was different concerns we were mitigating to settle the sample and mushrooming. So we modify what we do all the time. In order to, we were able to modify all of that, and that's very common. Sampling and touching the surface of Mars when you're contacting is one of the hardest things, because that's where you're interacting with surface we know something about, but not a lot. And we've collected 8 sample cores from a variety of different rock cores and 1 atmospheric sample, and then we have some witness tubes. We take these witness tubes in order to have a baseline of the areas on Mars so that we're not taking organics and detecting them. in order to do all this, we've reconfigured things. And here I'm showing the number of commands we send on a sol, and this is for the first 200 sols, for different activities. So there's, helicopter, sample catching, and mobility, mostly showing robotic operations. And we do multiple of them on the same sol. So we have atomic primitives that we use. We can send hundreds or even more than 1,000 in a day. And then there's non-volatile parameters on board the rover which change the behavior of these commands. And so, for example, we might want to drive 1 meter between taking visual odometry updates, or we may want to drive less or more. That's an example of a parameter. We have 200,000 of those parameters on the spacecraft, and we need to then use techniques to simulate and configure. But we've realized over time that things are going to change and be different, and if your autonomy isn't reconfigurable, you may not be able to use it. But you don't want to expose that to humans. With that many commands, thinking about all that day after day for years, decades, there's going to be a lot of human error. So we plan very much in the abstract. We have multiple layers of abstraction for this. So you're seeing here how we actually drive. This is the real driving software we use at the highest level. So images from Mars are going to have holes. We don't get perfect data. And this, picking a location to say, that's the target I want to have my first waypoint go to. And you're picking very few. On the left, you're showing, it's shown only in the abstract, but you can see there's just a few parameters you have to adjust to do that drive. And the next leg, I want to do an autonomous drive, shown in the magenta, with a larger way disk, because autonomous drives, it's going to want to select its path more. And there I selected from here that this leg is an autonomous leg. But that's the level at which we actually expose the parameters. All of the other configuration happens more strategically. But at the same time, people are really good at certain things robots aren't. And you could spend all your time trying to have sensing on board that could do things. That may mean that you're not sending it to Mars because it requires a lot more capability. So we use people strategically, and here's an example of that. So when we are driving autonomously, we actually have people do a path that is a suggested path that the rover might follow. It can divert away from that if it finds obstacles. The other thing is that our autonomous navigation is only detecting geometric hazards. It doesn't do textures, but there's a lot of sand, and we don't get a lot of, we use stereo vision, it doesn't get a lot of good registration. So we use these red geometric shapes as keep out zones for the rover to keep out of it, and the green is keep in zones. And then we have uncertainty, whereas the rover is driving, there's uncertainty accumulated, so we expand them as it's driving. So we use the combination of human and rover in the way that allows us to drive long distances with it. So tactical rover planning, we get the data from Mars, analyze what happened, whether the rover did what we expected it to do. Then the science teams gets together to say, what is the next thing we want to do given what we learned the previous day? And then we build the drive and send it. This is showing the drive we did actually to go deploy Ingenuity. We were looking for a really flat location, because at that time, we didn't actually know what its capabilities were. And this is the planned drive to try and go and drop off Ingenuity, which was strapped under the rover. So that brings us to talking about, there are certain times that if you're doing a mission within the constraint of a flagship mission, you can do the capabilities, but the risks need to be mitigated. Now, you want to take a leap in what technology you want to try, but there's an enormous risk. The way to have more autonomy there is to use technology demonstration, of which Ingenuity was an example. So Ingenuity was under the rover, powered by the rover, until we dropped it off. And once it dropped off to the surface, it was going to have to recharge with its own solar panel. So that was an exciting drive, because you really needed to drive off of Ingenuity, else if it didn't power, it might not have survived. But it has, since then, accomplished the first powered flight on another planet. The atmosphere on Mars is 1% the atmosphere on Earth. So flying on Mars is like flying at 100,000 feet on Earth, which no rotorcraft has done. And so this particular flight, it's going to take off and go to 5 meters above the surface, and then it's flying out to 50 meters downwind and going to go out of the frame. This image is being taken by Perseverance, mass cam camera looking at the rover, and there's a lot of coordination. Also, there's just certain size of imaging it can take, so the timing of timing the flight and getting all of that imaging in order to be able to see the flight that it did. So when Ingenuity is flying, it's using its navigation camera and tracking the surface, but the waypoints are sent from the ground. And when it comes down for landing, closer to the landing, about a meter off, it uses just IMU. And that's actually been useful because there was a time when it was doing science investigation where it dropped a frame and entered into an oscillation mode. But because it switched just to the IMUs before landing, it safely landed. So there are a lot of these conservative mechanisms of what could go wrong and planning for that that are important in this as well. So it was meant to accomplish 5 flights in the baseline mission. It's done 28 flights, and it has flown 6,900 meters and flown up to 12 meters. And the longest flight it's done is about 704 meters in 161 seconds. So Ingenuity is still going. And at the bottom are images taken with the camera before landing of the variety of different locations it's landed. There are times when it's landed, and you look at it taking off, and there's like sand coming off of the legs because it landed in so much sand. So it's light enough, and it's been able to fly in a lot of different environments. So I thought, I would end with, there's a lot of new people here, I'm told, so I thought I'd end with something fun. So what I'm going to end with is how we take this image of the rover and helicopter on Mars. So many of you probably know how we take this, but if you look at this image, what you don't see is a robotic arm. That's because it's taking the picture. The robotic arm and the microscopic camera at the end of the robotic arm, which is the Watson camera. We have a Sherlock instrument, so the Watson camera goes with it. But the Watson camera, we hold it out on the port side of the rover and point it at the rover's body to take an image. But we don't get to send specialized hardware to Mars to do things like this that we decided we wanted to try. It's designed for science. So it's designed for taking close proximity images of rocks on the surface of Mars. So this is an image of a target. It's 5 centimeters across. That's what it's designed to do. So a single picture just covers a small portion of the rover's body. So we took, for that particular image, 62 images. And once we figure out the arm configurations to do that, it's very repeatable because it's rover relative. But because we have a 5 degree of freedom robotic arm, kinematically, we have to keep the camera eye in the same position for all of the frames. We actually have to move the arm quite a bit between those frames to hold the imager in the same spot. To take that image, the robotic arm is doing a lot of motion, even flipping the shoulder to go from frame to frame. On Perseverance, we had a problem, which was that we had this massive bit carousel on the front of the rover, and the arm would collide with it, and we couldn't easily find a position which we could keep the camera in the same spot more manually. So, and the other problem is that the turret is much larger because it's carrying a bigger payload. Perseverance carries 70 kilograms of science payload. So we decided to throw simulation at it. So this is the simulation we use to drive the rovers, and it can take imaging. So we took the frames and mosaicked them together and ended up with this portrait. And it was a little bit different perspective because it's generated by a computer, not trying to optimize for what we would like to see in a self-portrait. So we decided to modify the position so we're not actually keeping the camera in the same spot, but moved it along the camera bore side to get rid of the collisions, and we ended up with this simulated portrait. So that worked out well, and we also wanted to capture this image that you're seeing of the arm moving. It's because the mast is taking a picture of the arm as the arm is taking a picture of the rover. It's like 2 photographers taking images of each other. And we also wanted to have sound because we had never had sound of a robotic arm moving on Mars. So we're trying to do all these parallel things, and that was one of the reasons doing this was more challenging early in the mission. How we get the 2 different pointing is we just take 2 extra frames around the head of the rover's mast, and we stitch them together to get the look where the rover is looking at the observer or at the Ingenuity. The problem was that very early in this mission, we wanted to have Ingenuity fly, because it wasn't clear if this really light spacecraft could survive the cold Martian night, and just the thermal variation. That is one of the hardest things on what we send to Mars, is just the variation of the temperatures it has to go through. So we had to very quickly go to the place we were going to observe Ingenuity after dropping off, and it fit in just in parallel with what Ingenuity was doing, releasing its blades and doing checkouts. So on Sol 45, we were still on Mars time, operating in synchronous with Mars. The day is 40 minutes longer, so we come in at 10 o'clock at night. We send everything up by 6 o'clock in the morning, and we're like, well, we're going to have the image tomorrow. We come back the next day, which was a 9:45 at night, and this is what we got. So it had taken the top frames, because we take those first, but there had been a fault. The reason is that we had just done some very basic checkout of the robotic arm, and we wanted to fly the Ingenuity and then go and do more checkouts and complete the mission, because we really wanted to get to the flight as soon as possible. So some of the fault protection was set very tightly, and we do a comparison between the resolvers and the encoders, and it had tripped. We were able to diagnose that and send the commands back, and got this picture, which you see, and that's how this image was taken. It's the only picture of the rover and helicopter in the same frame, because they have to maintain a 45-meter distance, because Ingenuity is a technology demonstration, and you can't risk the prime mission, the rover. So in terms of what comes next, we recently had a decadal survey. So NASA commissions the National Research Council to say what we should do for the next decade. And so they come up with a plan for what we're going to do from up to 2032. And in that, the highest priority is Mars sample return. So Perseverance has collected these samples and cached them on Mars. And the next mission is going to land and collect those cores, transfer them to a capsule. We're going to launch from Mars for the first time, rendezvous with an orbiter in Mars orbit, and then bring them back to Earth, which will be the first time that we will have brought samples from Mars back to Earth. There's also a lot of missions in the next decade that are going to the moon. There is a commercial lunar payload program, so NASA and a lot of commercial companies are building robots to go to the moon, and this is on the path to, in the future, going to Mars. So you're going to see a lot of robots on the moon as well. The other thing that was really highly prioritized was Enceladus and ocean worlds, where there's a crust outside, but under that there is an ocean that could harbor signs of life. And this is a mission which is one of the technologies that we're working on, is a snake robot to go to Enceladus, crawl into one of the vents of Enceladus, and take samples there. And that will be a mission that needs to be fully autonomous. So some of the capabilities that we're now more comfortable with, because we are testing them on Mars, are going to be absolutely critical for us to be able to have missions where they're just so far away that you're not going to be able to operate them with human intervention for the duration in which the missions can last, because it's such a harsh environment. There's also a spacecraft being sent to Saturn's moon Titan, and it will fly and land in certain spots, so it can fly from spot to spot and land on the surface and collect science observations that way. And I wanted to mention that there are a lot of people who work on this, and there's two organizations that I work with. One is JPL Robotics and the Mars 2020 mission. And there's I'll end with leaving the websites where I'll take questions, but I'll be outside, and you can find, if you search for me, you can find me, ways to contact me. But also, there's a website for Mars JPL and the robotics, where you can find a lot of other people who are doing a lot of interesting work. And we are a very collaborative organization. We work with a lot of students and university and commercial partners. So it's always great to work with people on new things that we might be interested in doing, particularly in the technology demonstration that enable future missions. So thank you.
All right, that was awesome. Thank you. So we have time for questions. There's a microphone here if you want to ask questions. Also, I will have the chat open momentarily, and I'm happy to take any questions remotely. Yeah, go ahead. Do you want to use the microphone? No, behind you. Turn around. Right there.
So yeah, thanks for this very interesting talk. Just a very quick question. Like, we saw a lot of walking robots at this conference, and I think they're reaching out now a level of maturity where they're also interesting for space. So my question would be, like, what is the plan of NASA of using one of these robots, maybe going up, going down craters or going up highlands or things like this?
Yeah, so we do have technology that people are working on. We do have technology that we're working on that has walking robots. And there are certainly places that walking robots would be better. And the challenge really is the reliability and the payload capacity. Those are the two things for the mission we care about. But I think it would be really cool to do a legged technology demonstration. And that would be really great to do. So I think that is something that we expect we will be doing in the future, because it allows you to get into places like, the DARPA Sub-T challenge is showing, that are harder to get to with other forms of mobility.
Thank you very much for the very motivating and informative presentation. So personally, I work in a field called for robotics, but there is a number of other fields like evolutionary robotics, self-configurable robotics, that from the point of view of technology demonstration, we are still pretty much behind, let's say, I don't know, TRL3, TRL4. And we always use, space as a motivating factor for our proposals, at least in the EU. I'm sure it happens also in the US for an NSFF. Like, these robots will make it one day to Mars for exploration and so on. And my question for you is, like, are you keeping an eye from the NASA perspective to all these technologies that are not that advanced? And do you think that any of them will ever make it to Mars? So is there any concept about, like, I don't know, bio-inspired? I saw some pictures, some videos at the end. Any of these fields, would they ever reach the technology readiness level to make it to Mars?
Absolutely, actually. That, I was showing you at the end the two different, like we have the robotics organization and the missions. The missions are targeting specific missions, but that's the job of the robotics organization and the research programs, is we look all the way from TRL1 all the way to, TRL9. And so we are looking at very early technologies, because if we're not able to do, we're just going to be doing things the same way. So that is very much an aspect of what we do. And so some of this comes through work that we can do through the size of the organization we have. We have, about 200 people, but at the same time, collaborations allow us to expand on that. So that's why we're really interested. If you have an idea that's way further out than something we might be doing, that's interesting as well. So absolutely. And Ingenuity is an example of that, right? It was not something that, even after all the testing we'd done on Earth, just because you can't test in that way, it wasn't clear if it was going to succeed. So you can do these missions where you're not compromising the tech demo, but it's going alongside another mission to a place that you need to test for the next level of autonomy. So hopefully, we actually would like to see tech demos on every flagship mission.
Thank you very much.
Hiya, thank you so much for the talk. I was just wondering if we could go back and watch the landing video now, if it was working, or if we could find it somewhere online.
Oh, yeah. The landing. Yes, that is absolutely there. And if I can't get that one working, get in touch with me, and I will send you a link, in fact. Yeah. I will try to get that. And it's really cool. So I was on the rover side on the day we landed because, eating the peanuts, which are the lucky peanuts for JPL, because I wasn't involved with the landing, but if something had happened to the rover, I was there. And this image came, the image that this ends with, is there a way? I wonder why that's, maybe if we go out of presentation mode, we might be able to play it. So he'll try to get it, but it was really exciting for us because we've done this kind of landing before. We've just never seen it. So we stayed there late because the image we get is a HazCam, and when that came down, it was so clear. Like, I think we were just like, wow, we have a rover. It looks intact. So that was pretty cool. So these are cameras that we also aren't used for the science. They're meant just for the landing. Yeah, I'm not sure what's going on there. Otherwise, come by later and I'll show it to you on my laptop. If not, yeah.
Thank you very much.
Hi, yeah, I was intrigued by the autonomous targeting that you talked about, and I'm curious how you manage the trade-off between like safe paths, which I assume are probably uninteresting, and more interesting paths that have more targets along them, but maybe more dangerous for the robot to traverse.
That's a really great question. So yeah, the autonomous targeting, that's actually, we all have different modules. That's a module that I program, so I'm particularly fond of it, but for Perseverance. But we don't do that. So right now, so we are not actually solving the problem of removing the maximizing the opportunity of finding targets that are interesting. We are going to a destination of interest, and along the way, if we opportunistically find something interesting, we take an image of it. And that matches what the mission would like to do, because they want to speed along and get to where we're trying to get to and not waste time diverting. But in the future, if we were doing extremely long drives, you might consider making a small detour to go get that science observation. We can actually autonomously, we also have capability to do terrain evaluation, deploy the arm autonomously and take images with the camera at the end of it. You could do something like that and then drive away. So that's something that I think I'm particularly interested in investigating, and that's another kind of thing where we would do on research side. We may explore projects with students and other things to explore that, and then it gets to the stage where we think it has probability, because every single image we take on Mars is available publicly. I know there's some of you here that I work with where it can be challenging to get all the camera models and everything, but we're working on that because we would like more people to be able to use the gigabytes of data that we have.
Great, thank you.
We still have time for more questions, but I thought we'd take one from
Oh,
online.
yeah, sounds
All right, so this one's good. What are the most likely mission-ending events? Are there a small number of candidates or a wide array of possibilities?
So there's actually a lot of fault protection we build into the spacecraft, because we haven't so far, one of the mobile robots had a mission crash. Mostly it's dust storms that have gotten us and other reasons. But there are a lot of possibilities, because literally every day you drive, if you weren't doing some of the checks, you could collide into some bulger, disabling the communication or hitting the antenna or something. But at the same time, we have a lot of protection. It's really hard for a single person to screw up and really cause a problem, because we have simulations that run the instance of all the commands. So we may do the rover driving software, and we're doing our simulation in our drive software, but then we take all the commands from everywhere and run them. Then we also have the ability where if the spacecraft has a problem, it knows what are the series of things it should do. Science, it'll stop doing science. It might stop the rover. AutoNav can actually try to recover from some of the no path and work its way around. And another one that seems really simple but works really well is just resetting. When we get to the point where we encounter a situation we don't know, we reset so we are in a known state on the spacecraft. That allows us, and this has happened to our spacecraft before and happened recently with Ingenuity when it lost its power, was it comes up at a time and it doesn't know what time it is, what time it should talk to Earth. We are not listening at the time it's trying to talk. So then we sort of hunt for it and listen for it at all the times it could possibly be waking up. So we have a lot of these protections, but most mission ending, I would say, would be related to power, that you get so cold, your avionics get so cold that you just never wake up.
I can't tell if I'm horrified or relieved to discover that NASA's strategy is the same as the rest of us. Unplug it and plug it back in again. Go ahead.
Thanks. As you know, there are thousands of PhD theses on the context of Mars sample return. Right? What are the critical elements that are missing, technologies or software or whatever, that are missing for Mars sample return? And maybe you can say some words about the collaboration with ESA in that context.
Right. So actually, Mars Sample Return was a mission in collaboration with the European Space Agency. In fact, ESA is building, so the way the mission is, it's evolving a lot. Literally week to week we have reviews and it's a different mission concept. But The mission involves landing a lander landing. We're going to be doing very pinpoint landing, but we've got a lot of technology. I feel pretty confident about that. And then it's the next technology of robotic arm actually collecting the samples. And there is some talk about having Perseverance be the backup. So it's actually going to collect the samples out of Perseverance. And that's going to be really interesting. Two completely separate mobile, landed platform and a robot, and you're collecting the samples. So that is one of the challenges. Another one is if anything drops and other ways. And there are other concepts. We, will likely have a helicopter, and, the helicopter might, be a rover helicopter, and then, you can collect samples with it. These are all these things being looked at. And so I think the challenges there are more of manipulation and of very precisely inserting a tube into the Oz, of collecting it from the surface. So very detailed manipulation, I would say.
Thanks.
Hey, thank you so much for your talk today. I thought it was really cool. I heard you mention that the Mars rover uses VIO for drift correction. And I was kind of wondering, the kind of challenges you see in a featureless space, like, the Mars surface, and how much you trust VIO, and if there are other modes you have for drift correction built in.
That's a great question. So, we are using visual odometry we take a picture, we drive, we take another picture, and we try to feature match to know how far we've gone, because just the odometry doesn't tell us, but it's featureless in a lot of places. It's amazing with the tuning the parameters of the visual odometry, where we can still get scree. It just needs a few of the features. So we've done pretty well, but lately, we're at Hawksbill Gap at the base of the delta, and there's a lot of sand there. We have seen some VO issues there, but we can also point visual odometry to point in the directions as we're driving where we are looking. We are looking at techniques, and there's some people in the audience who's looking at techniques where we could do texture detection. So instead of just using feature detection, in a way, be able to tell when we are in areas and avoid them with autonomous navigation. But visual odometry is absolutely critical. It's become so fast with the second processor we have. We almost don't drive without it because of the precision that we want with it. It's worth it. What we do is the number of visual odometry failures we allow. So if I know I'm in a featureless terrain, I might say I can tolerate a few my state estimation drifting by a couple of steps, and I'm going to just allow for that margin to my obstacles, because it may not converge. And then we don't fault. We just keep driving, even if it doesn't converge.
Thank you so much.
Want to take another one?
Yeah, sure.
Okay. As the Ingenuity flight has succeeded, is there scope for guided collaborative navigation between aerial and field robots in the future?
Right. So that is something that we are very interested in also doing. So right now, we use Ingenuity images on the ground. Rover drivers use it. So we'll use it to be again, sandy terrain, as the previous question was asking. But I can look at the image from the helicopter and drive through it. But it would be great if we could actually coordinate with the rover and helicopter. Some of the challenges, and this is something I'm actually particularly interested in as well, is there's the helicopter, but there's actually, so it has more processing than the rover. It's got a Snapdragon on it. The rover has a 133 megahertz processor. There's a base station on the rover, which is how the helicopter talks to the rover, which also has a computer on it. So very interested in using that computer to do rover's processing as, for example, like you were saying, to try to do some coordination. The problem is this was never designed to happen. And so we used the only port left. And so there's a really slow serial port between the rover and the base station. So if you were trying to transmit images, you'd have to trade off how much of an advantage it is to transmit them. But there's techniques we could use, and that is something we're actually looking at, definitely, to do.
Hey, thanks for the great talk. At the beginning, you speak a little bit about the parts and where the parts which are basically damaged throughout the mission. And I was wondering, do you also have a 3D printer or idea to have, for example, like a 3D printing hub in the Mars in the future, which could substitute these wear parts?
And that is, so the question was about what are the parts that degrade. So that really is what causes the problems is when a hardware part degrades on Mars. Really, the only thing you can fix is software. Like everything becomes a software problem once you're on Mars because you can't change the hardware. But we have come up with ways to reconfigure some of the hardware. On Curiosity, the drill feed mechanism stopped moving. And so when we were drilling, we could no longer move the feed. And so we started doing what's called feed extended drilling and all of the sampling based on that. Opportunity had a toed-in wheel, Spirit had a wheel. So we've had rovers and we adapt around it. But 3D printed is something that I think there's some research looking at, and the question just becomes, what materials would you send and how do you do that? How do you then install the part in the location that's needed? But I think that would be quite interesting to do. But there's a lot of those kinds of challenges is how do you, after it's printed, use it?
Okay, thank you a lot.
Last two, I think.
Okay.
Hi, thanks for the great talk. I had a quick question. So I saw that you were solving a lot of engineering challenges like perception, planning, controls, navigation. So in any part of your stack, are you using learning at all, like reinforcement learning or learning for controls or learning for perception?
Right, so that's a good question. There is technology we're certainly working on which uses machine learning techniques to do some of that texture mapping and all. In the algorithm you saw for the feature detection, there is actually some learning used offline for the parameters. Like, it's unintuitive how you should tune the parameters to get the scientists what they want, but we would like to use more learning on board. And part of the problem has been, one, data. We are usually going into areas where we don't have large pre-existing data sets, but there is techniques that we can use. And the second has been processing. It has to be computationally really cheap, and memory. So those variables, but that's changing with things like Ingenuity, and so I think these are very much possible for something like sample return.
Thank you so much.
Final question.
Thank you for a great talk. My question is, so we don't have complete knowledge about certain regions of interest in Mars beforehand. So is the rover able to adapt to finding new regions of interest once you deploy the rover there using information from its sensors?
Right, that's a great question because, the images we have from Mars are taken from orbit. We have the high-rise camera on the Mars Reconnaissance Orbiter, and those are great images. But something, I should have had a picture. When you look at something from Mars, from orbit, it looks like this tiny little speck, and you're on the surface, and it's completely different from that perspective. So every drive we do, at the end of the drive, we take imaging. So you see, we stopped the drive earlier. It gives us the local perspective at the end of the drive. So we are constantly discovering, and that's manipulation only occurs in images we take, workspace imaging at the end of the drive in the context of the rover, because there just isn't the resolution. We never drive just on orbital imagery without autonomous navigation. We wouldn't do a directed human drive in it. But yeah, every drive we discover something new and we take those images.
Thank you so much.
And they're online. You can go look at all of them.
All right, well, thank you for the questions. Sorry we didn't get to all the questions on the online forum, but Vandi, I'm sure will be happy to answer any questions you might have throughout today. But let's just say thank you for this inspirational presentation.
So, there may be a talk here, but I'll be outside. If anybody has more questions, then I'm happy to chat.